Hello, my name is Brian Harrison, and today we will be evaluating the effects of friction on a cylinder on a ramp. The experiment will involve rolling a cylinder down a ramp and measuring the time it takes to move from the top of the ramp to the bottom of the ramp. We will do this by taking a slow-mo video and looking at the exact frame that the cylinder is released and the frame that it rolls off the ramp and measuring the change in time and taking the average. Analytically, we will determine the time it takes for the cylinder to roll down the ramp. Well, let's move to the experiment. So here you can see the ramp, and this chapstick will be our cylinder. So we will set it up here and let it roll down. Here is the table of the tabulated experimental results. You have the diagram over here that demonstrates the ramp. Phi here is not directly known, but we can use these two values, the inverse cosine relationship, to find phi. Now we can look at our experimental results. As you can see, all of it teeter around 0.4. In fact, the average value I received was that time was 0.38 seconds. We can use dynamics to analytically determine the value of t and compare it to our experimental result. All right, now is the time to determine an analytical solution to the time that we experimented on before. So consider this rolling cylinder. We're in a 2D plane here, just to simplify things. Of course, you have the same ramp, the same phi. You have the cylinder. The center of mass is point C here. It's got a gravitational force pointed down. At the point of contact, there's a friction up the ramp and a normal toward the center of mass. It is rotating at the speed theta dot. The x direction is down the ramp and the y direction is 90 degrees from the ramp. So we can assume that the mass is 4.00 grams. That is the mass of the chapstick container. The moment of inertia about the center of mass of a cylinder is 1/2 mr squared. Now the key to all of this is the idea that the cylinder is rolling. We will be able to check this later. But first of all, we need to set up our equations of motion. So first, the force in the x. We have an mg, a component of the mass times the gravity in the x direction, minus the friction. And that's equal to just mass times acceleration, Newton's second law. Now in the y direction, we have that the normal force minus the other component of the gravity force should equal 0 because the cylinder is remaining on the ramp. It is not bouncing up and down. Last, the sum of the moments about the center of mass. There's only one force that's not directly on the center of mass, that being the friction. So if you do R cross F, determine the moment of friction, which we have as negative d over 2 times F, that must be equal to the moment of inertia of the object times its angular acceleration, which we call theta double dot. The negatives are just for the sign, since we're rolling opposite of the positive z-axis. We can solve the third equation, the moments about c, for F, which we yield 2 over d times the moment of inertia times the angular acceleration. Then we can plug this into equation 1, the force in the x. We can then substitute in equation 4, we have that the acceleration is d over 2 times the angular acceleration. Just plug that right in. Now we solve this for theta. Now if you plug in that the moment of inertia of the cylinder about the center of mass is 1/2 mr squared, the angular acceleration to 4 times the gravitational constant over 3 times the diameter of the cylinder times the sine of the angle. Now if we plug this back into equation 4, we can find that the acceleration is equal to simply 2/3 times the gravitational constant times the sine of the angle of the ramp. But before we check what our time is, we need to verify first that we are actually rolling. So using this theta dot, we can plug this back into our equation for the friction. And we find that the friction is 1/3 mass times the gravitational constant times the sine of the angle of the ramp. Now from equation 2, the forces in the y's, we can clearly see that the normal force is equal to mass times the gravitational constant times cosine of phi. If we use the relationship, the friction when rolling is less than or equal to the coefficient of friction times the normal force. The coefficient of friction must be greater than or equal to 0.0975, which is approximately 0.1. So here we have the engineering toolbox. This is a website that is quite phenomenal at finding tabulated data of certain engineering constants, variables, other things like that. Here we are looking at the coefficient of friction. We were looking for polyethylene. Here we go. Polyethylene on polyethylene. This is because I used a plastic lip balm. We also used a plastic ramp. So the polyethylene on polyethylene, it yields a coefficient of static friction of 0.2. So which is double what we needed to ensure rolling. Therefore, the friction is sufficient to force the cylinder to roll. Using our value for acceleration of 2/3 times the gravitational force times sine of phi, we then plug into a kinematic equation. This is because gravity is not changing, so the acceleration must be constant. So we use that delta x is equal to v naught times t plus 1/2 a t squared. Because we release the cylinder from rest, v naught is 0. So solving this equation for t, the time is about 0.435 seconds. Using the average time from before, we can calculate a percent error, and we yield a percent error of 11.8%. This is quite high, but there are many factors going into why this percent error could be so high. For example, simple measurement error. Another error could have arisen from a calculation error. And then there could have been a couple more experimental errors. When taking the videos, perhaps the times were taken a little bit off, which created a large difference. But the key takeaways from this experiment is the idea that dynamics can accurately predict the behavior of rolling object. This could be important in a wide variety of applications, from a car to a Mars rover. Knowing how the wheel will behave under the effects of friction, how well it will roll in certain scenarios, and whether or not the wheel will slip, leading to a loss of control, are all very important aspects of aerospace engineering, in which dynamics provides the perfect solution.